Hello, I'm Josh Salomon, Senior Principal Software Engineer at Red Hat, work as an architect in the Ceph team.
Hello, I'm Orit Wasserman. I'm a Senior Principal Software Engineer, and I'm OpenShift Data Foundation Architect at Red Hat. Today, we're going to talk about a very interesting topic, asymmetrical storage implementation. During my career, I always learned that we need to make sure that the storage system is symmetric. But surprisingly enough, there are use cases that you can use asymmetrical architecture and gain lots of advantage, like reduce the cost and improve the performance. We're going to start why we care so much about symmetry in software-defined storage, and then move to asymmetrical software-defined storage architecture and focus on an example with Ceph. So what is software-defined storage? First of all, it's software only. And the idea is you take the software and install it on commodity hardware, commodity servers, commodity disk from hard drive to NVMe, even persistent memory, and use standard networking, IP-based, usually TCP/IP. Then you get a distributed, reliable, and highly available storage system. And one of the main advantages is it's very elastic. It's very easy to expand it. You want more storage, you add more disk. You want to even also add more computation power, you add servers with additional disk. And it's so easy to expand the storage. It makes it very, very scalable and very good use case for cloud and cloud native application. Usually software-defined storage systems scale from several nodes, in case of Ceph 3, to up to hundreds and thousands of nodes in a single cluster. Here's an example of distributed software, distributed SDS architecture. Usually the client connects to the storage through a standard network. And they can use standard network storage protocol like for file, NFS, and SMB, and for block, iSCSI, and Vimeo Fabric. They can also use specific clients for the storage. For example, from Ceph, we have KRBD, who provide a Linux block device, and KSFS, who provide a file system without any need to change the application. The storage system is a group of servers also connected with standard network, each maintaining and managing its own local devices to make sure the data is reliable and resilient to failure, because our hardware is unreliable. We need to replicate and make sure that we have several copies of the data. In case of replication, the data will be written to several different nodes in the cluster, but read can be done from any copy. In many cases, we support eraser coding because it's much more capacity efficient, but in this talk, we won't go into eraser coding. A little bit about Ceph. Ceph is an open source project, software-defined storage, quite mature, more than 10 years. And Ceph uses commodity service, IP networks, most commonly TCP/IP, and support any kind of disk from hard drive to system memory. A single Ceph cluster can support all the different storage needs from object, block, and file. It's very highly available, resilient, and has self-healing, and very scalable. This diagram shows the different components of Ceph that provide a different protocol. You can get, with CephFS, you get a distributed file system. With RBD, you get a virtual block device, and with Rados Gateway, you get S3 compatible object storage. All those components use at the same underlying infrastructure, Rados, reliable, autonomous distributed object storage. Rados provide the reliability, elasticity, and distribute the data across the nodes in the cluster, and provide resilience with replication and erasure. We'll go on to important component of Rados. We have the monitors. They are the cluster manager. They have the cluster view and map and handle clustering events. The monitor uses Paxos as a consensus algorithm, and we have from 3 to 5 node monitors in the cluster. Then you have the OSDs, the smart storage daemon. They are providing the I/O to the clients. We have lots of OSDs in the cluster. Most common is one OSD per disk, but you can partition a disk and have the OSD only serve that partition. We have from tens to thousands OSDs in a cluster. Ceph use calculated placement called crash. And crash is a very important part of Ceph, as it makes sure that the data is distributed uniformly across the cluster, and also it can support failures, as crash is topology aware. Because it's calculated placement, we don't need a lookup server, and every client can do and calculate the placement itself. So a client connects to the Ceph cluster. He gets the cluster layout from one of the monitors. Then in case of I/O, he can do the calculation and find the group of OSDs that have and handle the object data. And then he can go directly to those OSDs. For read, he can go to any OSDs. And for write, he needs to go to the primary OSD. So why do we care so much about symmetry in software-defined storage? First of all, symmetry is not limited to software-defined storage. It's relevant in any storage system. But I think in software-defined storage, it's more important. Software-defined storage has a variety of possible configuration that we support, different hardware, different components you can enable or disable. This flexibility makes it harder to keep off symmetry. Also, as we allow the system to grow over time, each time you expand the cluster, you usually use the latest, newest hardware, which will be a bit different than the existing hardware in the cluster. And as we are working on Ceph, this is our domain, software-defined storage. What kind of symmetry aspect we have for the storage devices? First of all, performance. Each device type has different IOPS, throughput, latency. Also, they change during the lifetime of the device and the load on it. Then we have different technology, media, hard drive, or SSDs or SMR. It could be also how we connect to the storage, SATA versus NVMe, SCSI, and so on. What is the load on the device? During the lifetime of the system, there will be different load depending on the workload running and using the storage. Size of devices. Different vendor have different size as they use different over-provisioning percentage. And also newer devices will have larger size. If in the past, you usually can get 1 tera NVMEs, today, most commonly you have 4 tera NVMEs, and if you use QLC, you can get to 8 and more. And we need to care about how we fill the devices. If we won't fill the devices in the same rate, we'll get the system full because we are using replication. So if, for example, we have 3 devices, one gets full, we cannot write anymore. So we need to make sure that the fill rate is the same on the devices in the system. And for performance, we care about the weakest link in the chain effect. If you take a system with 100 devices with 200 IOP each, if you make sure you have enough clients and balance the workload and distribute it across all nodes and does everything correctly, you can get up to 20,000 IOPS, get the max IOPS from all the devices. But if one device for some reason will be slower, could be a malfunction or another problem, in that case, In the long run, the system won't get to the 20,000 IOPS, but can only produce 10,000 IOPS only. The weakest link will dominate the performance of the system. So we need to make sure that we can keep the symmetry, especially from performance perspective. Additional benefit is symmetry is management. It's easier to manage the capacity of the system. It's easier to manage the performance of the system and make sure we can, for example, have quality of service to the different clients. It's much simpler to configure a symmetric system. And it's easier to validate that everything is fine, the configuration is correct, and the software is validated. So I think I convinced you it's very important to have symmetrical software-defined system. And so we care about it in our system. We do a lot in Ceph to balance the load across the different nodes, to make sure the field rate is the same and is dependent on the device size. And lots of stuff. We balance in moving data around if you lose that. But is there a use case to break that assumption? Can we design an asymmetrical software-defined storage system, but it will still gain from breaking that assumption? And the answer is yes. And now switching to Joss, we'll talk about asymmetrical software-defined storage systems.
So let's start breaking our assumptions. As we discussed, when we develop software-defined storage, we can't control the hardware that is used by the users. The first use case that we started with was when we implemented Ceph on AWS. The first implementation used AWS EBS as the underlying storage. But this does not make a lot of sense. It is using storage system, Ceph, over another storage system, EBS. And while very reliable, it's also a very expensive solution. Then we thought of implementing Ceph on top of instances with local disk. But such instances keep the disk content only when the instances are running. The data is lost when you shut down the instance. While we could block the option to shut down instances from within our system, OpenShift console and CLI, we had no way to block such operation from an admin of AWS console. And therefore, our product management neglected this idea. This left us with a solution with technical advantage over EBS, but still too expensive. This is where the third bullet came into play, and we started searching for the lemonade. But there is another point. One of the advantages of software-defined storage system is the scalability. And the process of scaling a running system out puts a new challenge in front of us. The hardware we used when setting up the system may not be available anymore, or we can get better hardware for the same price. In many such cases, we want to add devices to existing systems and not replace a system with a new one. And this brings us also to various situations of asymmetry. So we have a Ceph system running on top of EBS, which is too expensive. Product managers do not allow us to use only instant storage as backing devices. And we started thinking on a hybrid solution, which is not symmetrical by definition. We have now two questions that we need to answer. One, is it worth it? How much money can we save? Two, how do we make the best performance of this hybrid configuration? Or how we extract the most from the dollars we pay for our system? In other words, how we can make the best lemonade from our lemons. So let's try to compare two configurations in AWS. The prices are updated for August 2021. First point, comparison is not simple. We are comparing apples to oranges in some sense. I took some assumptions to make things simpler, but it is not a simple calculation. I chose the smallest instance type from each family that provides a sustained network bandwidth, rather than peak performance, but no real guarantee about performance under long-lasting load. Even in this case, we can see that we have different characteristics in almost every dimension. Another assumption that we took is comparing to flat rate EBS volume type, GB2, which provides limited bandwidth. But for other types, price comparison is way more challenging. And last note is that when the devices are under full load, the network becomes the bottleneck. Yet I assumed the two M5.8XL instances provide the same performance as a single i3N.6XL instance. This is not fully accurate since this leaves a lot of extra CPU on the M5 instances, which can be used by workloads that do not require network, not a lot of access to EBS. But if we look just at the storage perspective, we see that the cost of M5 instances plus EBS is almost twice as the cost for local storage with the same capacity. Moreover, the local storage provides much better performance, both from latency and bandwidth perspectives. So what can we do with all this information? Before we start, let's review some facts on which we based our analysis. 15 terabyte of local storage has 10 times 4K IOPS and about 3 times the bandwidth relative to 15 terabyte EBS volumes of type GP2. For high load system, it is cheaper. Removing EBS volumes is a malicious and destructive act. Shutting down an instance is a legitimate action under some circumstances. Hence, we don't assume that a human removes EBS volume by mistake, but we can't ignore the chances of shutting down an instance with instant storage as a result of human error. EBS storage reliability is between 99.9% and full 5 nines for type IO2. For various workloads, we can assume these are reliable enough. Note that EBS is limited to a single availability zone. So if we want to protect from availability zone failure, EBS is not enough and we need additional protection. And just as a reminder, we talk here mainly about a replicated storage. So the read is served by a single device, while writes are served by multiple devices. And here is the main idea. Let the fast devices serve all the read requests as long as the devices are available. And on the right, replicate the data also to the more reliable EBS volumes. So for the read IOs, we use only faster devices, and we limit the use of slower devices to write IOs and reads when device error happens on the fast devices. So what can we gain from this configuration? The obvious things that reads are faster and the read bandwidth is wider. This is assuming the bottleneck is in the devices and not in the network. In any case, read is not worse than the old configuration with the same network bandwidth. And what about the writes? Well, we can't gain on the write latency, but we sure gain on the write bandwidth. The reason is that the devices with a lower bandwidth are doing only writes and use their entire limited bandwidth for writes, wasting no limited bandwidth on reads. So on reads, we are either in win or tie situation, and for writes, we always in a win situation. Having said that, there are some points to pay attention to. One, we need to factor network bandwidth here as well. If the network bandwidth is too small, it will become the bottleneck, and we may not fully load the devices. If this is the case, we may want to also use some other techniques, such as compression, in order to better utilize the network. Two, if you want to fully understand the behavior of the system, we should do analysis per our real-life workload and the way reads and writes are split in the system. This is beyond the scope of this presentation. Assuming local storage is not reliable enough, we have several options to implement replicated storage. Some examples are one replica on local storage, one replica on EBS, or one replica on local storage and two replicas on EBS. Or another option, two replicas on local storage and one replica on EBS. Each of these options has different costs and different reliability behavior. So how can we choose which one to use? There are several things that we should consider before deciding on a configuration. One, how reliable is the cloud storage? In AWS, there are some volumes with reliability of 99.8 to 99.9% and some with 5 nines. If the slow storage is reliable enough, we may not need two replicas on the slow storage. Two, Currently, AWS EBS volumes are available only on a single availability zone. If we want to protect against availability zone failure, we may want two replicas of the slow storage on two different ACs. 3, some data is less important and requires less availability and durability than other types of data. In this case, we may have less replicas. To summarize, we have multiple options to balance cost, performance, and reliability. There is no one correct answer. There are different options for different use cases. We may want to provide several choices to the users according to their workload and quality of service requirements. So here are two options for implementing asymmetry. The first one uses an attribute which is attached to each device and is called primary affinity. So what is primary affinity? It is a global parameter per device that can control the probability of this device becoming a primary OSD. These parameters ranges is 0 to 1. 0 means the device will never be primary, and 1 means that it will become primary according to the algorithm. Note, it does not mean the device will always be primary for every PG. So the first option that jumps to mind is to use the primary affinity attribute of OSD devices, giving all OSDs of local storage primary affinity of 1, and all OSDs of cloud storage primary affinity of 0. This means that no cloud storage-based OSD will ever be a primary OSD. This is exactly what we want, and it seems that this simple trick will solve our problem. However, this configuration can't guarantee that the other replicas will be on cloud storage devices, so we may end with all the replicas on local storage. We will see later when we can use this solution, but for our current use case, it is not good enough since we need to control the replicas on the cloud storage. So the next option is to have custom crush rules. This is a bit more complex, but only a tiny bit, as we will see in the next slide. So the first step, though, is to make sure that all the local storage devices have specific device class. It's assumed let's assume it's called local, and all the cloud provider storage devices have different device class that's assumed called EBS. There are multiple ways for attaching storage classes to devices, as well as mass change of these classes. So this is the rule for a primary on local device and the rest of the copies on cloud provider storage, EBS in our example. This rule will work for any replica count greater than or equal to 2. What we see here is that the first OSD is taken from class local and the rest with class EBS. This is a modification of the default replicated rule, and it puts every replication on different host. We can change a failure unit from host, but it doesn't make sense in public clouds, unless we want to put every copy in a different AC. There are some examples how to do that in Ceph documentation and in some blogs. If we have more than 2 replicas and we want 2 replicas on local storage and the rest in EBS, we can change the number 1 to 2 on the first choose leaf step. We started looking at a solution from a financial perspective when we wanted to take advantage of cheaper, faster, and less reliable storage in our system. Now let's look at the final solution from a different perspective. What do we see here from a system perspective? We have a distributed storage system. The data is protected by relatively slow storage, but every piece of data is persisted also to a faster storage. This looks just like a full-size read flash cache over the cloud storage. So we can now assess this solution from a cache perspective, but 100% capacity cache with no cache misses, unless, of course, we encounter some error in the system. Now, let's think about other use cases. Assume you have an existing HDD cluster and you want to upgrade to SSDs, but you don't have the budget for replacing all your devices at once. Assuming you have replica 3, you can start with replacing only 1/3 of your capacity with SSDs and use asymmetric implementation. The same is correct for older SSDs versus NVMe SSDs or any other storage type and newer, faster storage type. In other use cases, you may have a cluster with older HDDs and you want to add more HDD capacity. But now you can buy only larger HDDs with approximately the same performance. As we saw before, larger devices break the symmetrical load on all the devices because they full at the same fill rate. And they become bottlenecks since they get more I/O requests. If we can treat those as slow devices and make them non-primaries, we can get better performance than a symmetrical situation. In both these cases, and especially in the latter, we can use implementation that uses the primary affinity attribute of a device. This is because in these cases, all the devices are reliable. Hence, we do not care about the device reliability, only about the performance. And therefore, we don't care if we have non-primary copies on devices that are faster. So let's conclude. In many cases, symmetrical implementation for distributed software-defined storage systems is optimal. In practice, requiring symmetrical implementation, especially for software-defined storage, may not be feasible, either for financial reasons or for logistic reasons. When the system is not symmetrical anymore, we can have multiple choices. We can split the system into multiple symmetrical subsystems. This is by creating symmetrical pools. This works well, but does not fit all the use cases. For example, it does not fit expanding capacity of existing large pool. We can try to combine different devices into the same pool in a way that will maximize the performance of the system. This can be done by putting more load on the faster devices and less load on the slower devices. If the performance difference between the devices is noticeable but not dramatic, we can play with other values of primary affinity, not only 0 and 1, to maximize performance. This is beyond the scope of this presentation and depends on the specific devices and workloads. This is the end of our presentation. Thank you, and please take a moment to rate this session.